So far we have been looking at additive and abelian categories, and we looked at some of the properties of abelian categories. Yeah. Today we would like to study a class of abelian categories which is larger. Which has more properties, but it is a smaller class. Okay, and before we begin with that, see, our plan for the next couple of lectures is going to be identifying where abelian categories live. We will show in particular that all small abelian categories can be treated concretely. And later on we'll talk about a particular very strong class of abelian categories. They will be co-complete. Yeah, so it's a large class which contains all module categories and something related to that. And later on we will, like in the next lecture, we will try to see some homological algebra. Yeah, we'll start with the notion of an exact sequence today, but we will continue in that direction in the next lecture. So that's our plan. Fine. So let us look at this simple definition. Say that a sequence 0 to A to B to C to 0 of objects of A, of objects and morphisms of an abelian category A a sequence 0 to A to B to C to 0, let me call these F and G, of objects and morphisms of an abelian category A is said to be an exact sequence if, first of all, do you understand what this 0 is? Yeah, it is the 0 object, and 0 to A is the unique map, which is again the 0 of that home set, and C to 0 is also the unique map, which is the 0 of that home set. Okay, so this is said to be an exact sequence if F is a monomorphism, then G is an epi, and third one, that kernel of G is isomorphic to image of F. Okay, so normally if you have seen this definition of an exact sequence somewhere else, then you will say kernel of G is equal to. But here we are treating kernel and image as morphisms. So in the subobject poset of that object, middle object B, these two are isomorphic. Okay, so F is a mono. Now let us verify that actually at every internal object in this sequence, we are asking for exactly the same condition. What is the image of this 0 morphism from 0 to A? It is 0. And then F is a mono, which means kernel of F is also 0. Yeah. Similarly, at C, look at the image of G. What is image of G? Because G is an epi, so it is C. And what is the kernel of the next morphism C to 0? Whole of C. So therefore, the identity on C. Yeah. In both cases, it is the identity on C. So again, that is isomorphic. So at every internal node A, B and C, we have got the property that kernel of the next morphism is isomorphic to the image of the previous morphism. Obviously, we can't check it at 0 objects. Yeah. Later on in the next lecture, we'll see the notion of a chain complex and an exact sequence, long exact sequence, where we'll extend this on both sides to infinity.
do we mean by image? Is it like
Image is what we defined. It's the kernel of the co-kernel.
so the image of G will be G itself?
Image of G will be G,
Isomorphic.
yeah, isomorphic. Yeah, like identity map on C. It will be isomorphic to the identity map on C.
Okay, but the kernel of zero map is not.
Kernel of zero map will also be identity on C. Everything goes to, yeah, right. So this is an exact sequence if these three properties, or equivalently it is exact at each point, at A, at B and at C. Okay, that's what, like, we can also define the exactness locally. Okay, then I mean some simple observations which you, yeah, some remarks. So 0 to A to B is exact if and only if F is mono. Okay, the dual remark would be that B to C to 0, this G is exact if and only if G is epic. I mean, that's what I have written above. And yes, one more property that you might find interesting is that this identity map followed by some morphism is exact if and only if F is, no, F is 0. F is the zero morphism, because what is the image of A? Image of identity is identity morphism itself, and therefore it has to be the kernel of the next object, right? So kernel of the next object is, so kernel has to be everything, so therefore F is 0. And do you remember what we said? Okay, we will we'll use this particular remark in the next proof. So before that, let me give you the definition of an exact functor. So a functor f from A to B for A and B abelian is an exact functor, is said to be an exact functor if it takes short exact sequences to short exact sequences, if it preserves exact sequences. So notice something, so far we have talked about additive functors between pre-additive categories. Here we are not at all referring to the home sets. We are not asking that additive means that 0 should go to 0, then byproduct should be preserved. Nothing of that sort we are asking for. But that is all automatic. Yeah. So let us see that. So first, I mean, thanks to remark 3 above, what do we conclude? That F is the zero morphism if and only if the identity morphism is exact. And do you remember some result that we proved last time? When is an object the zero object? Let me scroll up. Home set is singleton, and we wrote something. Yes, I think it's here. Yes. So for an for a pre-additive category, an object is initial if and only if it is terminal, if and only if the identity is 0. Okay, so now use this, yes.
So that function you told like in this statement that has to preserve some property, right?
It should take exact sequences to exact sequences.
You are not assuming anything else like additive function or something?
No, I'm not assuming additivity.
Oh, that is just a function between categories, nothing else.
Yes. So, see, any functor will always preserve equations. And therefore, what does it preserve? I mean, look at these two results that we proved last time. That some object is 0, some object is the 0 object in a pre-additive category if and only if its identity is 0. And identity 0 is equality, it's an equation. So that equation must be preserved. Okay, so therefore, what will happen? That in the image also the same thing will be true. Identity is always preserved, right? By any functor. So thanks to this and remark 3, we can conclude that 0 objects are preserved. Yes, remark 3 said that you can fill up the details. Yeah, it's not hard. So identity is always preserved. So therefore 0 morphism is also like this is the only morphism. Yeah, so that is preserved. So therefore 0 objects are preserved, and I mean first 0 morphism is preserved, and hence 0 object is also preserved thanks to this particular result. Okay, later on look at what we said. The next result was that for any two objects the product exists if and only if it is the co-product, and if and only if the third condition, and third condition has nothing to do with categorical properties. Yeah, it only talks about equations, and equations are always preserved. So therefore F also preserves. If it preserves exact sequences, then this is like an exact sequence. Yeah, you take nu1 then pi 2, that is an exact sequence. 0 nu1 pi 2 0, that is an exact sequence, and similarly 0 nu2 pi 1 0 is also an exact sequence. And then you have these identities, so everything will be preserved. All the identities will be preserved by an exact functor. So therefore byproducts will also be preserved. So let me just write this now. Thanks to remark 3, F, an exact functor, preserves 0 morphisms and hence 0 objects. Okay, so similarly, I mean I can even if you assume one side, so therefore I mean what do we really need here? Therefore F is exact if and only if F preserves kernels and co-kernels. Yeah, 0 object, 0 morphism, everything is preserved. So what remains is only kernel and co-kernel. So an exact functor is only this. Actually, this is a definition now, that say that F is left exact if it preserves kernels. I mean, if it takes an exact sequence 0 to A to B to C to 0, to an exact sequence, 0 to FA to FB to FC. We do not ask for the last 0. That is left exact. So left exact always preserves kernels and right exact preserve co-kernels. So it's like 1/2 of the definition. A functor is exact if it is both lex and rex. Yeah, so left exact is usually abbreviated as lex. Okay, so I mean even 1/2 of it is sufficient.
So,
Uh-huh.
because products and co-products are bi-split exact sequences and equations,
Yes.
so any functor from an abelian category always preserves products and co-products.
If it preserves short exact sequences, then yes.
But to preserve
Split exactness, yeah, okay, yeah. So split monos and split epi's, they are always preserved. They are absolute limits and co-limits. Yeah, so therefore they are always preserved. So let me just write that. So recall that absolute limit and co-limits are the limits and co-limits which are preserved by any functor. You don't need to ask for them. We have seen many such examples. Yeah, the splitting of an idempotent, then split mono, split epi, and split co-equalizers in Beck's monadicity theorem. Yes, we did cover that. We did not cover the proof, but we did cover the statement. Yeah, G-split co-equalizers. Okay, so split monos, mono and epi, are always preserved and hence the exact sequences of the type, I mean, I'm just reminding you of what this is, the byproduct sequence. Yeah, A direct sum B, and then to B, this is nu1, this is pi2 to 0, and then in the reverse direction we have nu2, and in the reverse direction we have pi1. Okay, so are preserved by any lex functor, lex or rex functor. Okay, so therefore, what can we say? See, lex functor will preserve kernels, that we have seen, and lex functor also preserves byproducts. So in particular, it preserves binary products. So lex, therefore, lex implies Cartesian and rex implies co-Cartesian. Yeah, finite limit preserving. I mean, this is a regular category. Okay, regular category, abelian categories are regular, which means kernel pairs of morphisms exist. Kernel pairs means you take a morphism F, and with the same codomain you take another copy of F over here, and then you take the pullback. So pullback of F along itself, that is the kernel pair. And the co-equalizers of kernel pairs exist over here, and the definition is self-dual. Definition of abelian categories is self-dual. So therefore lex is precisely regular, I mean exact is precisely regular, but then it automatically gives you the other half because it is self-dual definition. Okay, so therefore what do we have? That exact sequences are additive Even left exact sequence, functors are also additive. Exact functors are additive. Left exact functors are also additive. Right exact functors are additive. But lex and rex are both something more. They preserve kernels and co-kernels respectively. So an exact functor is a bicartesian functor. It preserves finite limits as well as finite co-limits. Okay, good. Then let us look at one particular type. Yeah, this is the strongest possible type of categories that you can ask for. Strongest as in the sense that you want all the nice properties of the category of abelian groups to be present in such categories. Okay, so what are such categories called? Well, these categories are called Grothendieck categories. Grothendieck abelian categories is also another name. So Grothendieck defined them, obviously, as the name suggests. He did not call it Grothendieck abelian categories. So he gave a list of axioms AB1, AB1 op or AB1 star, the dual condition, then AB2, AB2 star and so on up to AB5. AB5 did not have a dual condition. I think, yeah, AB5 also had a dual condition. The AB1, AB2, AB3 and their duals, they together give you the definition of an abelian category. Yeah, so these are known as Grothendieck's axioms. And AB4 and AB5 are what we are going to write down. And then there is one extra property which is always nice to have. Okay, so let us define Grothendieck categories. So once again, I want to remind you that the purpose of defining Grothendieck categories is we want all the nice properties of the category of abelian groups to be present in this category. What do you know so far about the category of abelian groups? Abelian, okay. So Grothendieck category, let me say that. Yeah, the first one is that. Yes, and very smart answer that Grothendieck abelian categories are abelian categories. An abelian category A is a Grothendieck category if, okay, what about the category of abelian groups? Does it have some infinite limits or co-limits? It has all infinite limits and all infinite co-limits. In particular, it is complete and co-complete, but in particular, it has got all co-products. Okay, so the first condition that I am going to write down is that it has all small co-products. Well, when we assume that it is an abelian category, we already know it has got all finite limits as well as co-limits. In particular, we have got all co-equalizers because co-equalizers are same as co-kernels. So therefore, I mean equivalently, it is co-complete because all co-limits can be constructed out of arbitrary co-products and finite, binary co-equalizers. Okay, second property. Now this has to do with one lecture in the middle that we talked about, the commutations of limits and co-limits. What was the spatial property of the category of sets? Filtered, okay, filtered what? Filtered co-limits. Co-limit of a filtered shape commutes with limits of any finite shape. So finite limits commute with filtered co-limits. Okay. Now look at a short exact sequence. Short exact sequence has what? It has got a kernel and a co-kernel, mono and AP, and okay. So kernel and co-kernel. Co-kernels are obviously going to be preserved by by directed co-limits, filtered or equivalently directed. Yeah, we have seen that result. And actually, I mean, yeah, I should remind you that we have also seen that the same property, that filtered co-limits or directed co-limits commute with finite limits, it also holds in any category of finite ray algebras. So in particular, it holds in the category of abelian groups. Abelian groups are finite ray algebras. It's just one binary operation, one unary operation, and so therefore this property holds true in the category of abelian groups. We have to include it in the list. But we are not going to write that all directed co-limits commute with finite limits. We are going to write that a directed co-limit of short exact sequences, I mean short exact sequence or exact sequences that we wrote, it's also called short exact sequence, is again short exact. Okay, so now look here. Yeah, so we are taking a sequence. So let's say natural numbers is our shape. For 0, we have a short exact sequence. A0, B0, C0, then A1, B1, C1. And then we have AN, BN, CN. That's a short exact sequence. Then if I take vertically, if I take the directed co-limit of AN, vertically directed co-limit of BN and directed co-limit of CN, then obviously the last part, because it's an epimorphism, epimorphisms have to do with push-outs, or in this case co-kernels. Directed co-limits and push-outs or co-equalizers, they obviously commute because both are co-limits. So therefore there will be a last 0, but there may not be the first 0 in general, right? The first 0 has to come from a kernel. So the sequence of kernels is again taken to a sequence of kernels, which means, see, we never had to ask for finite products, because finite products and finite co-products commute. I mean, they coincide in the case of an abelian category. So therefore, directed co-limits automatically commute with finite products. So it only remains to ask that do directed co-limits commute with kernels, and that is what this property is saying, that it preserves kernels as well. It commutes with kernels. That's the only remaining thing. Okay, so this is AB4 and AB5. Okay, then these two properties do not have duals. And the third one, that it has a generator. Okay, so what is the meaning of generator? Generator means it's a separator, or equivalently it is a detector, a single object which is both separator or detector. So how do we do it? Let us recall it quickly. What is the meaning of a generator? It can distinguish between two parallel morphisms. So generator, so let us say G. So let me remind you of the definition, that G is a generator or separator, that is what I am defining, if for any two for any parallel morphism with F not equal to G, we have a morphism H from G to A such that FH is not equal to GH. Well, rephrase it, i.e. F minus G composed with H is not equal to 0. Well, what do we mean? Like, i.e., in this case, it will turn out that the home G A is non-zero for any A. Okay, so this is a transformed definition of a generator or a separator in a pre-additive category. Yeah, the home set has to be non-zero. There should always exist a non-zero morphism. So, for example, in the category of abelian groups, what is the generator? Z. Yeah, I mean for any A non-zero, obviously.
So this last condition, AG non-zero, is it equivalent to the existence of non-H?
In abelian categories, yes. Yeah, because we are just talking about abelian setting here. And dually, a co-generator would be something such that the other home set is non-zero. Home A blank C would be non-zero. Okay, so I mean, let me remind you, if you remember the definition of a detector. Detector was that if you have a mono which is not an iso, then there is a morphism from G to the target of that mono which doesn't factor through this mono. Now, if your category is balanced, then separator is a detector, and if your category has equalizers, then detector is separator. So last time we saw that every abelian category is balanced, and obviously it has equalizers because it has kernels. So therefore, detector and separator, there is no real difference. This is the definition of a generator. Yeah, that's what you have to use. So a Grothendieck category, if it has three properties. See, what is the main point of number 3 here? It has a generator, which means like every single abelian group can be written as a quotient of a huge direct sum of copies of Z. So same thing here also I can write down. Yeah, so this implies, I am writing it in bracket, that for any x in object of A, there exists a set I and a short exact sequence Gi to 0 to x to 0. Okay, what is G to the power I? It is the co-product of capital I many copies of G. Yeah, so there is an epimorphism from G to the power I to x. Okay, so this generator actually makes it so that the category is large, but it is not too large. You remember this statement? When did we use this? That it is large but not too large. In what context did we use this?
It's special adjoint function.
No, not special adjoint functor theorem. Class of sets, no. We don't want to talk about set theory here. GFT. What is GFT? Adjoint functor theorem, no. No. It's large but not too large. We said this for locally presentable categories. Locally presentable categories have got finitely presentable objects forming a set, and then every object of that category is a directed co-limit of finitely presentable objects. Okay, so that time we said this. So this third condition ensures that our category is not too large. The first one says that it is co-complete, and the second one says it has this desired property that finite limits commute with filtered co-limits. Yeah, so all these properties. So what will be examples? Yes, abelian groups, category of abelian groups. What is the generator? Generator is Z. And how do we cover any abelian group? How do we cover every abelian group, like as an epimorphism? We simply take Z to the power bracket X, yeah, and then send everything to every unit vector with only one non-zero entry to itself. Yeah, generator is Z. Then obviously we have seen the, I mean without proof we have seen that directed colimits and finite limits commute, and it obviously has all coproducts. This is a monadic category over this, so everything is created and for free. Okay. So another example is the category of R modules for any ring R. What is the generator? R. Yeah, R is one of the generators. I mean, of course, if there is one generator, doesn't mean there can't exist others. Yeah, but is a generator. Maybe I shouldn't write equal to, but is a generator. Okay, R modules also have the same properties. This is also nice. Then some properties for those who know about these things, that sheaves of abelian groups on a topological space. Power of a generator is also co-power, I would say, not power. Co-power means co-product of some index family. So sheaves of abelian group on a topological space, or sheaves of abelian group on a site, on a Grothendieck site. Commutative rings. I never said anything about commutative rings. No, why are you asking that? A single commutative ring. Category of commutative rings. No, category of commutative rings, that's not even balanced. Yeah, so if it is not balanced, it can't be abelian. Yeah, so obviously it's out of question. Okay, so sheaves of abelian groups, you probably don't know, some of you may know. So these are examples of this. And Grothendieck site is something I will probably explain in the last week. Are there any other examples for which abelian categories? Any abelian category? Okay, that's a very good question. So I'm giving you two different classes, but perhaps you don't appreciate them. Yeah, these sheaves of abelian groups are on.
Yeah, I mean, what I have seen are modules and sheaves of.
Yes, and yes, so then I will give you more examples. That's a good question. Then quasi-coherent sheaves on a scheme. Yeah, this is also an example of this. See, right now you are asking me for an example of a Grothendieck category, and Grothendieck categories have to be very spatial. So they have to have lot of properties, and that's actually our next goal. And let me write this. Any localization of a Grothendieck category with exact localization functor is also Grothendieck. So I am trying to give you some way of closing it under more, of creating more Grothendieck categories. But of course, I haven't defined what is meaning of localization. So that's going to be our next topic. So let me state what. So localization, those who have studied algebra, commutative algebra, let's say, they should be familiar with the concept. So consider Z. Then in integers, you consider all non-zero integers. Is the set of non-zero integers closed under multiplication? Does it contain 1? Yes. And what if you want to invert all these non-zero integers? Like multiplicatively invert all the non-zero integers, what do you get? Rational numbers. Okay, so basically this is called localization. Localization means you want to make something, some elements invertible. Some elements in that ring should become units. But, well, this is a category theory course, not an algebra course, so an element doesn't really make sense. We have to replace an element by an arrow. Yeah, and some collection of arrows should become invertible under a functor, and it should be the smallest such thing. So for example, when you talk about integers and localizing or inverting all the non-zero integers, then you can also construct real numbers. Real numbers also have the same property, but the smallest such thing is rational numbers. So whenever there is a ring homomorphism from Z to any other ring such that all non-zero integers have their images units, then there must exist a unique morphism from rational numbers to that given ring. So in this sense, this rational numbers is the universal such construction together with an embedding from integers to rational numbers. Okay, I said lots of things without writing anything, but this is the idea from algebra. Now, a ring is a single object pre-additive category. So therefore, now we want to invert everything possible, like some collection of arrows that we want to invert. Okay, so let me give you some different ways of doing this. Localization in categories. Okay. So let S be a class of morphisms in a category C. Yeah, here I am writing just usual Roman S. Yeah? Let S be a class of morphisms in a category C. Localization of C with respect to S is the universal functor C to S inverse C such that I will call it L, yeah, because I want to call it localization, such that given, let me write this such that, first of all, if F is a morphism in S, then L of F is an iso. Yeah, so for all F in S, L of f is an isomorphism, and whenever, so for any functor f from C to D that takes every morphism f in S to an isomorphism, there is a unique f tilde from S inverse C to D such that the following diagram commutes. Obviously, this is L, this is F, and this is D, and this is S inverse C, and there exists a unique f tilde such that this diagram commutes. So what did we start with? We started with a collection of morphisms which we want to invert. Now let us look at one particular example, then you will understand that there are ramifications of this. Yeah, it's not automatic. So for example, let's consider this. Let R be a ring and S be the class of morphisms in R mod that consisting of this. So any module you take multiplication by 2 map for any module MR. Left module I am denoting by writing R as a subscript. So x mapping to 2x, this map you would like to invert. Then what will happen to the map that is x mapping to 4x? If x mapping to 2x is always inverted, then x mapping to 4x, which is a composition of two such maps, then that will also be inverted. So in fact, all powers of 2 will be inverted. Yes, so automatically, so 2 to the n dot blank will also be inverted. Then there is also another ramification, right? I mean, here I am talking about 2 as 1 plus 1. But what happens to the map multiplication by 6? Well, multiplication by 6 is same as, now is isomorphic to multiplication by 3. You can always invert, like that effect is nullified now. So multiplication by 6 and multiplication by 3 will be similar. So if there is something which has, let's say, order 2, then it will get killed. I mean up to isomorphism, so you have multiplication by 6 map and multiplication by 3 map, and then there is a multiplication by 2 map in between. You just write a commutative triangle. Then this map is invertible. Multiplication by 2 map is invertible, so therefore their codomains, yeah, I mean that becomes an equivalence, not necessarily equality, but it becomes equivalence. So this is what, like, there are consequences of inverting some morphisms. So in particular, if F and G are two morphisms in S, then their composition, even though composition, if it exists, even though it may not be present in S, it will also become invertible. So composition of two invertible maps must become invertible. Then obviously any invertible map will remain invertible under any such thing. So you would like to add these properties. Understood? That you would like to say that the class of morphisms with respect to which we are localizing, that's actually a subcategory. And it should contain all the identity morphisms, because they are automatically going to be inverted. And this is the same thing that we talked about when we considered Z and non-zero integers. Yeah, that this set is closed under multiplication. Multiplication is composition. So this is a subcategory and it contains one, it contains identity. Right? So you can invert, like it's more logical to invert at subcategories which contain all the identities. And also the invertibles, well, we are not going to say anything about that. They will always remain invertible, but we don't have to specify. So just for the sake of talking about it, yeah, we will do this. Okay. Now look at this. I'm going to use a slightly different notation over here. So for example, I'm not using any different notation, but suppose elements of S will be, right, it could be a set or it could be a class, will be denoted, are denoted by zigzag arrows. Okay, so these curly arrows. So suppose I have this, I have three objects like this. Then this particular map A to B is invertible in the target. And I have one more such pair of morphisms. Then what will be the composition of such things? Like this, then in the localized category, this B to C via going inverse along, let me call this F1 and G1, F2 and G2, and I already said that this wiggly arrow is in S. So this particular map G1 composed with F1 inverse, this particular composition is a morphism in the resulting category because F1 will be invertible, right? So G1 F1 inverse is a new arrow in the resulting category. So we are trying to describe what happens in S inverse C. So this part will be invertible. Then similarly, we should be allowing compositions of such things. Yeah, two such things. Well, finitely many such things, because if it's a category, we have to close it under compositions. So in general, imagine what happens. I'm given two fixed objects, and then in between I can take finite zigzags of this kind. One inverse, then direct, inverse direct, inverse direct. I can take finite zigzags. So imagine how many morphisms there will be. Even if we start with a locally small category, in between, like we are allowed to choose any arbitrary C, and C could be coming from a proper class. It could be a very large collection. So therefore, like all things, all finite sequences of objects and finite sequences of these morphisms, that collection could be large. Yeah, it could go very easily, it could go out of control. So what I am trying to say is that these compositions of zigzags between two fixed objects could form a proper class.
Won't some of the composition
some of the compositions will get identified clearly, but a priori you cannot have any control. Do you have any control that it will always be a set? I always need to take, so these kinds of figures, these are called roofs. Okay, this ABC, that is called a roof. Yeah, I mean, it looks like a roof. A pair of morphisms where one is invertible, one is in S and another one is not. So these finite sequences of roofs, well, they can choose any intermediate objects, and that is a problem. Yeah, so therefore compositions of zigzags, they can form a proper class. So immediately, like even if SC is locally small, S inverse C need not be. You understand? So the things can go out of control very easily. So we want to control it somehow. Okay, so this is one thing that I want to emphasize on, and then there is another thing which also you should know about. So I am going to use a different color. If C has, let's say, a terminal object, a zero object, let's say, we are talking about abelian category. If C has a zero object and the unique morphism from 0 to A, this belongs to S, then zero morphism is always preserved by any functor, right? So, so therefore, zero object is preserved by any functor, so nice enough functor. So this unique morphism became an isomorphism. So what happened to A? A also becomes zero object, isomorphic to a zero object. So therefore, when you want to localize certain arrows, then you are also killing certain objects. So there are two different ways. Yeah, so set of morphisms in algebra, yes, localization with respect to a set of morphisms. Non-zero multiplicative closed set, yeah, containing no zero divisors either. Yeah, I mean, you generally ask for that.
So, like, even in this case, we should reject the zero morphism.
No, we don't reject anything. This is we are talking about localization in categories. Yeah, and in category theory, we generalize everything possible. So we are also going to kill some objects. Yeah, so and hence in localization, thus in localization, LA will be isomorphic to 0. So we are killing some objects. So the data, therefore the data of localization can also be provided using objects which get killed. So there are two ways of providing the data for localization. Either you provide a set of morphisms which will be a subcategory, yeah, which contains identity morphisms, or equivalently you can, like if your category has nice enough structure, then you can also provide some collection of objects, some class of objects that you wish to kill. Okay, so now if you understood all these ideas, I am ready to state how to do it for a particular class of morphisms. Is it okay?
Can this help us to control
These both methods are actually equivalent. In the case of abelian categories, these are equivalent. Yeah, so it's not different. Let me start with the definition. So This is Gabriel and Zisman. You have seen the name of Gabriel already. So Gabriel and Zisman, this is left multiplicative system. Okay. So what is a left multiplicative system? You start with a collection of, so S is a collection S of morphisms of an abelian category A is called an LMS, left multiplicative system, if first of all the identity belongs to S for each A in OBA. Second property, it should be closed under composition. So if F and G belong to S and G composed with F is definable, G composed with F exists, then G composed with F is also in S. Third property, okay, it says that given this diagram, given any such diagram, there exists, so given ABC, a roof with F in S and G is arbitrary morphism, there are H and K. There are H and K morphisms of A with K in S such that I can complete the diagram. So A, F, G and then H, K. Such that this diagram commutes. So what exactly are we saying? Kg is equal to HF. Yeah, so from something from the left hand side, like if you try to read it some different way, that F inverse G, then that is same as HK inverse. Yeah. So left and right we have to worry, like usually when you study localization from commutative algebra, then you don't need to worry about these things. Everything is commuting. And the fourth property, yeah, this will also take care of zero divisors, etc., like whatever you want. So the fourth property is also interesting. So given a parallel pair F and G together with some morphism S with S such that Fs is equal to Gs, there exists some T from B to D. I mean, this is a curly thing, such that TF is equal to TG. So if this parallel pair can be equalized, weakly equalized on the left by a morphism, by an invertible morphism or morphism in this multiplicative system, then something similar happens on the right as well. Everything is about duality. Yeah? If left thing happens, then right happens. If you are given a roof, then you have this sink kind of shape. And dually you can define a right multiplicative system. The first two properties will remain as they are. The last one, like if you are given a sink, then you can add a roof so that it is complete. The parallel morphisms have to be in S. And given a parallel pair, if it is weakly co-equalized by a morphism in S, then it is also weakly equalized by a morphism in S. Okay, so right and left both systems, and then left plus right, it's just multiplicative system. And that is the definition that you see in ring theory, in commutative rings, commutative algebra. Okay, so why do we do this? Yeah, this left multiplicative system, or this calculus of fractions as it is popularly called. Yeah, calculus of fractions, why do we need this? Well, first of all, people wanted to generalize these common ideas from commutative algebra to non-commutative algebra as well. And then algebra, once you realize that a ring is just single object pre-additive category, so you bring everything to morphisms. So this particular calculus of fractions is quite useful in the following construction. So now for such a, so given, I mean, I'm just going to talk about a multiplicative system. You can say anything, left or right or both. Given a multiplicative system, I mean, here I will talk about left, S on a category, on an abelian category A, define a new category S inverse A as follows. So the first thing that we need to do is define its objects, describe its objects. So objects of S inverse A are same as objects of A. We do not change the objects at all. Yeah, there is another way to do it, like by shrinking the objects, but we are not going to do that here. Objects of A and morphisms now. So morphisms from in S inverse A between A, like A and B, are diagrams of this kind. The sinks, sorry, this should be C. Okay, are equivalence classes of pairs of morphisms indicated on the side, on the right. Okay. So see, what we started with was a left multiplicative system, and what we changed it to, like we gave some axiom for a roof, but we actually took a sink. Okay. So this is, I said, equivalence classes of pairs of morphisms indicated on the right. I have to describe the equivalence relation. Yeah, so subject to the equivalence relation, I mean, this you have to verify that it is indeed an equivalence relation. So, see, I can write A and B, then I can write C1, then this is any morphism, and this is any morphism, and this is C2, and this is also another sink. So, these two sinks are said to be equivalent. This is F1, G1, F2, G2. If there exists this diagram between F1, G1 and F2, G2 defined by the existence of F3, G3 and let's say H and K. So, I am going to use a different color because I can. So, this is another such sink with morphisms H and K defined like this, so that all four triangles commute. Okay, so this looks like a lot, but what this is trying to do very simply is it will try to say that 2 by 3 is 4 by 6. Yeah, that's what we are trying to do here. Nothing different is happening. Yeah, here please don't get confused, like 2 by 3 and 4 by 6, they are all arrows. Yeah, so you can have multiple representations for the same rational number. Yeah, so this is that. So subject to this equivalence relation, well, we are also have to, like, we are defining a new category. So what is the identity? So identity of A is, can you guess? 1 sub A and 1 sub A. Yeah, so A to A, it should be a sink and both of them should be identities. We do not change anything. It is the equivalence class of this. And what is composition? So composition is, well, I will say A to B and then to E. This is C. Then this is D. These are two wiggly morphisms. So if you are given such two things, what can you do? You get a roof and you complete that roof by using that property to a sink. So there will exist this blue diagram, and then the equivalence class will be of these two, like A to F and then E to F. That equivalence class is what your composition is. That's why we added this property. And while checking that this is indeed an equivalence relation, whatever we wrote above, you will also use property 4 of left multiplicative system. Okay, so there is lot of checking here, but in these lectures, I am just going to give you an idea of things. Any questions so far? One last thing remaining about this, that we are given S and we constructed S inverse A, it is indeed a category. Can we describe the map like the functor from C to S inverse C? What will, so this functor, the localization functor, so called localization functor L. So L from C to S inverse C is defined by A mapping to itself, B mapping to itself, and this F mapping to what? Very good. And the equivalence class of this. Yes, we cannot just say a single pair of morphisms, but an equivalence class of pair. Yeah, so that is the map. Now, whether it is embedding or not, I mean, whether it is fully faithful or not, that will depend on S, your situation. In general, it is not. And then what will be like for a given functor f, what will be f tilde? We want this diagram, yeah, I mean C to D also, if that is given, what will happen with S inverse C?
A to B via F and A to A via
1 sub A? Yeah, I mean, see, you have to describe a map like a functor f tilde. So it will take an object A to what? Object A to FA. Yeah, FA. So, and a morphism, where will it go? A morphism in S inverse C is the equivalence class of that. So it will go like the non-S part will remain as it is. You map it to FA to FB, and the invertible part, like some morphism in S from that sink, that will go to not identity. It will be mapped to the inverse of this morphism in the image. So given, yeah, for the universal property, given f from A to B, sending each morphism in S to an iso, define f tilde from S inverse A to B as follows. You send A to FA, yeah, you don't change anything because you had to land in B. Then you have this particular sink F, and then you have something over here, let's say little s, which is in S. So this one will also be sent to FC, but then this middle morphism, the equivalence class of this morphism will be sent to the composition. You take FB as it is, this is FF, no problem over there, and this morphism will be the inverse of Fs because it is defined. Yeah, that was the property, that Fs is invertible. So this is localization. Yes.
The left side is a morphism in S inverse C, which is from A to B, the object.
Left side of what is a morphism?
This is a morphism to morphism.
Yes, morphism to morphism, yes.
Left side is a morphism in S inverse C.
Left side is a morphism in S inverse C. It is the equivalence class of this. You pick any representative and then you do this. And then you have to show that actually it doesn't depend on the choice of B. I mean, A and C are fixed. B is different. You can have multiple things in the middle. Right? So, therefore, you just have to make sure that it doesn't depend on the choice of representative. And that is where this diagram will come into play, the equivalence relation. Yeah, there is a lot of verification here, but it is routine verification. It's important that you understand the idea.
Sir, what is the inverse of F?
F doesn't have an inverse. Fs has an inverse.
No, I am asking, suppose, suppose S is in capital S.
S is in
then
capital
what is
S.
the inverse of S in S inverse C?
Yes, that's a good question. What is the inverse of S in S inverse C? Maybe I should write it. Okay, so that's a really good question. So given f from A to B in S, yeah, so we want to see whether it is really invertible. How do you embed it? Like, then the corresponding morphism in S inverse C will be? Yes, 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 correct. So the image of f in S inverse A is this equivalence class.
B to B via 1A and A to B via
A, this is F, and then 1B. This equivalence class. Yeah, its inverse is you tell me.
A to A via 1A and A to B via F.
Yes, so the equivalence class we had to start at B, then I will take identity on B to B, and then I will make this F okay. So this is the multiplicative inverse. You can verify that it is two-sided inverse, right? So this is so it has universal property, and each morphism in S actually got inverted, right? So this is one way of doing localization, and this is economic. Because of this left multiplicative system, so calculus of fractions, we could accommodate lots of things. We could avoid talking about sequences of sinks or sequences of roofs. Yeah, any such sequence can be converted into only one sink. Yeah, so that's the important part here. If we have some extra data present in S, then lots of things become easy. Now, I already promised you that there is another way of converting, of killing objects, and that's also a way to localize a category. So this is our second way of doing that. So a Serre subcategory, by the way, I mean, I did not emphasize on this enough, but we are talking about two of the greatest names in 20th century in this lecture. Grothendieck is like the biggest name in 20th century, and Serre, yeah, J.P. Serre. Yeah, so a Serre subcategory, S, yeah, I mean, here I am going to use this curly S of an abelian category is a full subcategory whose objects satisfy the following property. So actually, whenever we talk about Serre subcategory, then we are only really interested in the collection of objects, the class of objects, because it's a full subcategory, so morphisms will automatically be there, whose objects satisfy the following property. Yeah, for any short exact sequence, zero to A to B to C to 0 in A, B belongs to S if and only if both A and C belong to S. Okay, so what in words, what it says is that whenever you are given an object in the Serre subclass, then its subobjects are also there. A is a subobject of B, and quotient objects are also there. So this subclass is closed under subobjects and quotient objects. and simultaneously it's also closed under extensions. So extension means that if given C and A, B is an extension of C by A. So it is closed under sub-objects, quotient objects and extensions. These three properties. Okay, and it can be expressed very succinctly in just one line. That for any short exact sequence this happens. Okay, now define a class of morphisms corresponding to this to be all those morphisms F from A to B such that the kernel object, which I am going to write like this, kernel object and the co-kernel object of F, they belong to S. Okay, so kernel object. So here what I am using really is this, that given any F A B, I have a short exact sequence, namely kernel F. This is simply the inclusion, this is 0, and then there is a quotient onto the co-kernel object and then 0. I am using this slightly long exact sequence, yeah, slightly longer. It's not exactly short, it has 5 internal terms. And this is like classic kernel F and this is co-kernel F as the morphisms, and these are objects. So what I am saying is that this particular sequence is going to turn, this particular morphism F will be an isomorphism if its kernel and co-kernel are both in S. Now see what happens when you take the image under localization. Kernel F will become 0 and co-kernel F will become 0, and isomorphic to 0 in the localization. So therefore, in between we have exactness. When do we have this exactness? It is 0, F and 0. That is exact if and only if F is an isomorphism. Yeah, epi and mono, because the category is balanced, so this is an isomorphism. So therefore, F will become an isomorphism. So I defined MS. Okay, so now, so therefore define the localization of A with respect to S written A mod S as the localization functor from A to MS inverse of A. Yeah, if you want to kill certain objects, then you might as well make these MS morphisms in MS as isomorphisms. So this is the localization. This is Serre localization. Any questions? I can talk a lot about this, but in this limited time, I just want to give you an idea of what this is. Yeah? But if you have any questions, yes.
What is the motivation behind this?
Because many times we want to kill particular objects. So as I said, like it doesn't matter whether you choose to make some objects isomorphic to 0 in the localization or make some morphisms invertible. So there is a way of also going back. Yeah, given if your category is abelian, then given a class of morphisms, you can also describe which objects you are going to kill. So, well, yes, kernels and co-kernels of those morphisms, and there will be some ramifications. So there are lots of things here. Yeah, I mean, some keywords if you want to search are hereditary torsion theories, orthogonality classes. Yeah, then I mean, Serre subcategories, and obviously this just ordinary multiplicative systems. If you want to know more, you should Google these things. Hereditary torsion theories, orthogonality classes, injectivity classes, orthogonality classes, these are all related terms. Okay, why did I define this? Yeah, because I said the class of Grothendieck categories is closed under localization. So I want to give you, in fact, I want to give you one very interesting result here, and it shouldn't be surprising that it was proven by Gabriel and Popescu. This is a Romanian name, Gabriel Popescu theorem. In this area, actually, there are many Romanian names. Yeah, Diaconescu in category theory. So every country has some specific things. Yeah, this Central Europe is more popular for abstraction. Yeah, Hungary is popular for combinatorics. Then Poland, Czech Republic, they are popular for set theory and logic categories. Yeah, similarly Romania. So Gabriel Popescu theorem. Gabriel was a student of Grothendieck. Yeah, his PhD thesis had lot of interesting things. So Gabriel Popescu theorem, let me state that. So A is Grothendieck with generator G. I mean, sorry, I should say suppose A is Grothendieck with generator G. Let R be AGG. Do you understand what R is? It's a single object pre-additive category, so it's a ring. Okay, so I can talk about modules over this ring. Okay, then A to the category of right modules, which I can write as this functor category. Then over here I can take the home functor at the generator. Then it will have a left adjoint L. I mean, AG blank is fully faithful. Yeah. Then AG blank. Then there exists this diagram with L exact. Okay, so what exactly am I saying here? That there is a diagram. So let me try to unravel some of the things. So AG blank is fully faithful. Do you remember, if right adjoint is fully faithful, then what do we call the left adjoint? Reflection. Yeah, reflector. L is the reflection. L is the reflector. And moreover, I said, so this is also called, reflection is also called a localization. If, yeah, and so a reflection Li is called a localization if L preserves finite limits. Okay, so once again, coming back to the original idea that we have a right adjoint, The left adjoint always preserves what? Co-limits. Yeah, co-limits are present, all co-limits are present on both sides, so it preserves co-limits. So in particular, it preserves finite byproducts, and as a consequence, it preserves finite products. So you only need to, like when we say that L is exact, we only really mean that L preserves kernels. We don't really ask for anything. Like this is extra. Yeah, normally it will preserve everything apart from kernels because it is a left adjoint. But here what we are saying that every Grothendieck category is a localization of a module category. I mean, left or right doesn't really matter, does it? ROP or left modules over R are right modules over ROP. So left and right is not important, but every module, every Grothendieck category is a localization in this sense, yeah, in this highlighted sense of a module category. Next time we will open with some properties of Grothendieck categories, and we will also prove Fried-Michel embedding theorem. It's a short proof, yes.
So we have another notion of localization here.
Yes. So this will also be a localization. Yeah, every such localization, that's a really good point. Yeah, I mean, I'm not talking about two different things. The localization functor with respect to a Serre subcategory, that will always give you this. Yeah, so you should, I mean, you will need to read a lot before you can understand with respect to what class of morphisms or what class of objects. But a simple idea, I will tell you, the category of all left exact functors from a small, from a ring to this, yes, let's say AOP, maybe I will write it. An example, so if you remember Cartesian or Lex functors from a small abelian category, this is small abelian. So Cartesian or Lex, yeah, to AB, yeah, these are additive functors. And on the other side, we have got the full functor category, R of AB. Yeah, then obviously the Lex functors embed inside this. And you also have a right adjoint. This is basically Gabriel-Ulmer duality, but the enriched version over AB. Yeah, I'm not saying anything different. This is I and this is L. So what is, so normally we will have this kind of map, right? A1 cross A2 blank. And then we will have A1 blank cross A2 blank. So these are functors. These are home functors, so they are objects on the right hand side. And there is some morphism between them, and we need that in Lex functors this morphism becomes an isomorphism. So you have to take the orthogonality like classes, class with respect to such things. You want this morphism to become an isomorphism, right? In Lex. So therefore you have to take this these classes of morphisms like of this kind. Then you also encode, and this is a small set, obviously, yeah, because A is small abelian, and that's how you construct this kind of localization. Okay, we will use it next time. Let's stop.